Hi, let's discuss space complexity of an algorithm. I already discussed time complexity of algorithm. For running an algorithm, how much time we require, that is called as a time complexity. Whereas for running an algorithm, how much space or memory is required, that is called as a space complexity. Space complexity is a function describing the amount of memory, or you can say space, an algorithm takes to execute the algorithm. How much extra space it requires rather than the input for executing an algorithm is called as a space complexity. There are two types of algorithm. One is non-recursive or iterative algorithm, another is recursive algorithm. We'll find space complexity separately for non-recursive algorithm and for recursive algorithm. As in case of time complexity also, we treat differently non-recursive algorithm. We found time complexity by summation method or by frequency count method. Whereas for recursive algorithm, we found time complexity by using back substitution, recursion tree or master method. Let's first discuss non-recursive algorithm. In case of non-recursive algorithm, how much extra space required to execute the algorithm is called as a space complexity. Let's consider this is a memory space, and for an algorithm let A is a array and this is the input given. If to execute that algorithm we need some extra space, then this extra space is called as space complexity. Whatever input is given, without that input how much extra space we require to execute the algorithm, that is called as a space complexity for non-recursive or iterative algorithm. Let's understand through an example. Example 1, it's for finding max element from an array, and as a input one array is given. Now we'll consider max value as a of 0 means first element. Then for I equals to 1 to n minus 1, do if ai greater than max value will be ai and return max value. Let's consider this is the memory, and as an input array A is given. Its index is 0 to n minus 1. Now for this statement max value will be A0, so max value will be this part, this is our A0. Then for I equals to 1 to n minus 1, we'll create another memory for I. Let this is I. Initially I will be 1, next I value will be 2, next I value will be 3. Like this it will change n minus 1. So in that same space of I value will change from 1 to n minus 1. Now if a of I greater than max value, then max value will be a of I and return max value. So for running this algorithm, we just need one extra space for variable I. So space required will be 1 and space complexity you can say order of 1, as we just require one extra space for variable I. But for this algorithm, time complexity is big O of n while space complexity is big O of 1. We just need one extra space for variable I. Let's discuss another example. One array is given as input and we are taking two variables. One is I, another is b of n. B of n is a array of size n. Then for I 1 to n minus 1, b of I will be a of I. Means we are transferring data of array A to array B. Then we will return array B. Suppose this is the memory space and this is our array A. It contains element from 0 to n minus 1. Then for executing this algorithm, we take one extra space for I and we'll create another array B. Now what we'll do, we'll transfer A of 0 to B of 0, then we'll transfer A of 1 to B of 1, then we'll transfer A of 3 to B of 3 like this. Whatever data of array A, that will transfer to array B. Now how much extra space we require? We require one space for variable I and we require n space for array B, as B size is n. So total we require n plus 1 space, n for array B, 1 for variable I. And here input is array, so that is not the extra space, that is already given in input. So extra space required is n plus 1. For b of n, it will be n. For variable I, it will be 1. So space complexity will be big O of n, while time complexity will be also big O of n. For this algorithm, we need extra space for variable I plus for array b. For array b, size will be n. For variable I, size will be 1 space. That's why space complexity will be big O of n. We need n plus 1 space, that we can write big O of n. Let's discuss how we can analyze space complexity of recursive algorithm. For recursive algorithm, we need a stack. So how much stack space is required for executing a recursive algorithm? That is our space complexity. Or we can say number of stack space required in control stack or runtime stack for push or pop of activation record called as space complexity. I already discussed what is activation record, what is control stack or runtime stack in compiler design. For each function, we store a activation record into a control stack. This is our control stack. For each function calling, we'll push one activation record into control stack, and for each return, we'll pop one activation record from the control stack. Let's understand through example. First example, it's for factorial function f of n. If n equals to 0, return 1, else return f of n minus 1 multiplication n. Let me analyze this algorithm. Let me consider n equals to 4. So f of 4, that will be f of 3 multiplication 4. F of n minus 1 multiplication n. Then f of 3 will be f of 2 multiplication 3. Then f of 2 will be f of 1 multiplication 2. Then f of 1 will be f of 0 multiplication 1. Now f of 0, if n equals to 0, return 1. So this will be 1. 1 multiplication 1, it will be 1. Now f of 1 value is 1. So 1 multiplication 2, f of 2 value will be 2. Then 2 multiplication 3, f of 3 value will be 6. Then 6 multiplication 4, f of 4 value will be 24. This is a recursion tree. Let me execute on stack. Now initial will push f of 4. F of 4 equals to f of 3 multiplication 4. So from this f of 4, we'll call f of 3. Now we'll push activation record for f of 3. F of 3 equals to f of 2 multiplication 3. So again we'll push activation record for f of 2. F of 2 equals to f of 1 multiplication 2. Again we'll push activation record for f of 1. F of 1 equals to f of 0 multiplication 1. Again we'll call f of 0. F of 0 value is 1, so we'll return 1 from it, means we'll pop activation record for f of 0. Now here 1 multiplication 1, it will be 1. Pop activation record for f of 1. Then we'll pop activation record for f of 2. Then we'll pop activation record for f of 3. Then we'll pop activation record for f of 4. When n equals to 4, we need 5 stack space. This is 1, 2, 3, 4, 5. 5 stack space for push or pop of activation record. So for n equals to 4, we need 5. For n, we need n plus 1 stack space. N plus 1 stack space means space complexity will be big O of n. So how much stack space we require for executing the algorithm is called as our running time in case of recursive algorithm. Let's discuss another example. And for this algorithm, time complexity will be big O of n. I already discussed how to find time complexity. Here recurrence relation will be t of n equals to t of n minus 1 plus 1. If we'll apply the master theorem 1 multiplication n, it is big O of n. Let's discuss next example, algorithm do n. If n equals to 1, return 1, else do n minus 1, again do n minus 1, then call b. Let me take n equals to 3 and draw the recursion tree and stack execution for n equals to 3. Now for d3, do 3, that I'm writing d3. For d3, we'll first call d of 2, then d of 2, then call B. Let for B we require just constant time. Next from D of 2 we'll call D of 1. Here again we'll call D of 1. From this D of 2 we'll call D of 1 and here we'll call D of 1. So this is the recursion tree. Let me execute on stack. Now from D of 3 we'll first call D of 2. This part we'll do later. Now from this D of 2 we'll call D of 1. When n equals to 1, return 1. Now we'll return from this, means we'll pop this. Again from D of 2 we'll call D of 1. Now again we'll push D of 1. This D of 1 is different from previous D of 1. Now we are pushing for second D of 1. Again n value equals to 1, so we'll return, we'll pop from this. Now this is also done, we'll return from this, we'll pop it. Again from this D of 3, we'll call this D of 2. So we'll push D of 2. Then from D of 2, we'll call D of 1. Next we'll return from this, we'll pop it. Again we'll call D of 1. Again we'll push D of 1. Then we'll return from this. So we'll pop it. Then we'll return from D of 2. We'll pop it. Then we'll return from D of 3. We'll pop it. So for n value equals to 3, we require 3 stack space. So for n value, we require just n stack space. So space complexity will be big O of n, as we require n stack space to execute this algorithm. Actually, we are using same stack space for multiple push and pop. We are popping, again we are reusing that space. That's why for this we are using n stack space. So for this algorithm, we require n stack space. So we can say space complexity is big O of n. Now what will be time complexity for this recurrence relation will be T of n equals to 2t n minus 1 plus 1. I already discussed same example here. A equals to 2, B equals to 1 and f of n equals to 1. I am applying the master method. Now running time will be a power n by b. So 2 power n divide 1 multiplication f of n. F of n is what? 1. So it will be 2 power n multiplication 1, or you can say 2 power n. So for this algorithm, space complexity is big O of n while time complexity is big O of 2 power n. Here space complexity is less than time complexity. Here space complexity is equals to time complexity. It depends on algorithm. Space complexity may be equal, may be less than, or may be greater than time complexity. It depends on algorithm. Let's discuss what is in place algorithm and what is not in place algorithm. An in place algorithm is an algorithm that doesn't need an extra space and produce an output in the same memory that contains the data by transforming the input in place. However, a small constant extra space may be used for variable is allowed. Suppose this is the memory and input is a array A is given. Now this is the input. If we are executing the algorithm in this space, that is called as a in place. We may need some extra space, means we may need some constant space here, then that is called as a in place. If we are running an algorithm in that input memory space, or we may need some extra space, some constant extra space, that is called as a in place algorithm. So what should be that constant extra space? Maximum it can be big O of log n. So if space complexity is less than or equals to big O of log n, then that is in place algorithm. Means whatever input space is given plus maximum we can take log n space for running that algorithm, then that is called as a in place algorithm. So example of in place algorithm are bubble sort, selection sort, insertion sort, heap sort. These are in place algorithm. So it will execute its algorithm in the same input space. I'll discuss what are these. If space complexity is greater than log n, then that is not in place algorithm. So merge sort is an example of not in place algorithm, as it require big O of n extra space. I discussed 4 examples. First example it was big O of 1. This is a in place algorithm. For second, third and fourth it was big O of n. This is a not in place algorithm. When space complexity is less than equals to log n, it is a in place algorithm. When space complexity is greater than log n, it is not in place algorithm. This n value is greater than log n while 1 is less than log n. With this, I am finishing space complexity. Let's discuss one previous question. This question was asked in GATE CS 2009, question number 35. Tn equals to n for n value less than equals to 3, else Tn equals to Tn divide 3 plus Cn. And it is asking for time complexity and 4 options are given. Now you can apply directly master theorem on this. Here a value is 1 and b value is 3 and fn equals to c of n. Now we got a, b and function. Next we need to find n power log a base v. So n power log 1 base 3, it will be 0. 3 power 0 will be 1. So n power 0, that will be 1. Next we need to compare cn with 1. Obviously cn value is greater than 1. When function value is greater than 1, it is case 3. Next we need to check a fn divided b is less than equals to cfn. So a value is 1, f of n divided 3, that is less than equals to n. So it satisfies case 3. Now running time will be f of n. F of n is c of n. C is some constant. So it will be theta of n. It's present in option A, so answer will be option A. With this, I am finishing chapter 1. In chapter 1, I discuss algorithm introduction, then order of growth, asymptotic notation, time complexity, space complexity, and how can analyze recursive and non-recursive algorithm. I discussed different methods for analyzing recursive and non-recursive algorithm. For non-recursive algorithm, I discussed sum expression method plus frequency count method. For recursive algorithm, I discussed back substitution method, recursion tree method plus master method. For previous question of chapter 1, refer the previous question playlist. If this lecture is helpful for you, please like and subscribe. Thank you.